Science time. Please have your notes out. During science time today, we're talking about the solar system, which is a large part of science. It's a large part of our lives. I'd like if you would please write down the objective with me as I write it down. There's no reason for you not to be writing it down, because if I'm spending my time doing this, at least the implication, and now the direct explicit instruction is, please write down the objective. Which is, present arguments from evidence regarding patterns in the formation of the solar system. Present arguments from evidence. Someone's going to have to help me with the rest. I've already forgotten. Regarding patterns. Is that right? Yep. In the solar system, is that it? In the formation of the solar system. In the formation of the, I'm going to use this font, solar system. Nice. Okay, we got a couple of things to talk about the objective. One, I do agree with the verb phrase present arguments from evidence. I really like that. I don't use it very often as the objective. You'll see it is one of the science and engineering practices. You see that? Presenting an argument from evidence. Which one is that? Oh, engaging, it says, in arguments from evidence. Number 7 on science and engineering practices. I really like that one. That's a really important thing, and we do it. In my opinion, when you fill out the conclusion on your lab, you are participating in an argument from evidence. The reason I don't use this verb phrase very often, and I have used it here, is because a lot of people, probably rightly, associate this argument with like an argument. Like, you know, if you and your mom have an argument, that means something, right? If you and did you say your niece? Sure. If you and your niece have an argument, I don't know your life, Trey, but if you and your niece have an argument, that means something to you. Like, that has a social, a personal connotation. And it's not dissimilar to, but it's not the same thing as what we're doing in science. So in science, ideally, it is dispassionate, which means you're not like getting in someone's face and yelling at them as an argument, but you are presenting information that supports your claim. Remember this? I think you do this in English too. You remember this? Do you remember this? We do this every time on your self-check too. So you have a claim. We will make a claim regarding patterns in the formation of the solar system pretty soon. But you have a claim, and then it is for you to present evidence that supports that claim. And this process is called an argument. So you make a claim, which is a statement. You present evidence about that, and then you reason the relationship between the evidence and the claim. Why does this support this? And that process is called an argument. Now, wouldn't it be beautiful if every time you had an argument with your mom or your dog or whatever, it was as neat and cut and dried as this? Like, no, Mom, I would like to spend the night at my friend's house because X, Y, Z, and due to the fact that ABC, right? That would be a really nice way. But instead you say, Mom, I want to do what I want. And that's how your whole life goes. And then your mom says that basically back at you. And then the whole thing is what you would call an argument. But in science, an argument is the evidence that supports a claim and the reasoning that ties the two of them together. In this case, I have chosen to use that verb phrase, present arguments from evidence, because it's important, in my opinion, that if the claim is, as we'll say in a minute, that the solar system formed in such and such a way, that this is the evidence for it. Because it's not good enough to just say, that's the way it is. A lot of times in science, we say, effectively, that's the way it is. We often then say why, and we ask questions about it. But in this case, we're going to start with the evidence to draw the conclusion, the claim. And that's why, in your lab, your conclusion that you write is actually an argument from evidence. Does this make sense? Do you understand this? As another little side note, the reason I chose patterns of formation in the solar system is that, one, we see this in lots of different places repeating time and time again. That's what a pattern is. But also, that's one of the cross-cutting concepts. So now we have, in our objective, a science and engineering practice, a cross-cutting concept, and our content information, which is the solar system. So, that having been said, I'm going to write Well, it's just called the solar system. I don't know. I guess the title of this video is called "The Solar System and How She Formed." Doesn't have to be a she. I guess whatever you want to think about it. This is America. The solar system. Something really interesting about this, I think, is that in a lot of the mythologies, both the ones that you're familiar with and many of the ones that I'm familiar with that you may not be, the involvement of the creation of the universe is that there was chaos and out of that came order. And that's a really important thing because the evidence bears that out. That there is something like chaos and it becomes more orderly through a process. And in the mythologies, of course, this is a god or gods. And that's fine. As we said at the beginning of the year and as we've said several times since then, there's nothing wrong with that, but it's not necessarily scientific and that doesn't mean it's bad. It means that in science we try to present evidence from the real, I don't like that word, from the physical world, right? There's physical evidence and that suggests that this and this process did this. In my opinion, there could be in a person's mind room for both. That there is room for belief and there's room for physical evidence. And if you find that not to be the case, then you can, whichever direction, just let what I'm saying wash over you and at least don't chirp back at me. But the general trend of chaos becoming order is one, apparent in many world religions in their creation mythologies, and two, borne out by evidence in the solar system. And so to illustrate that, we have here first, I think someone did this in their lab. What might you say was the first thing, the chaotic matter that was before the universe, as evidence suggests? And we'll get to the evidence in a second. What was it in someone's lab? Yeah, yes, and dust. Thank you, T. Later we're going to watch this video. They're going to be like, why did he say it like that? The answer is Teak has a terrible case of laryngitis that he's trying to get everyone to have. And so there was chaos, the gas and dust. So we have a cloud of gas and dust, which we call, do you remember from your vocabulary, what's the term for this cloud of gas? Starts with protoplanetary. I'm going to say nebula. Am I going to spell it right, though? That's a real question. Protoplanetary nebula. Did I use the wrong term? Or Trey, is that why? Not Trey. What's this kid's name? Aiden. Maybe just planetary nebula. I think I've confused the terms protoplanet and planetary nebula. So let's just call it a planetary nebula. Scratch the proto, although we will come back to that. So the planetary nebula, we have a cloud, effectively, a chaotic cloud of gas and dust. And then evidence suggests, and we'll talk again, as I say, I'm really teasing you with the evidence, but we'll talk again about what that evidence is. The evidence suggests that slowly from that planetary nebula, something started to happen. And what was that? Yeah, so, okay, yeah, flattening first. So now we end up with next a disk, what is sometimes called an accretion disk. ACC, can't tell because of my handwriting, ACC RETION, an accretion disk. Swirling kind of, this is really important, and I actually meant for this to be a question, but swirling in a direction. It's kind of like if Luigi's at the pizza shop and he's swirling the dough around with his finger, or if the water going down your bathtub drain is circling. There's an accretion disk and it forms this kind of flattened out. Or if you have a water balloon attached to the end of a drill, ideally, if you have a regular balloon attached to the end of the drill, nothing happens. But a water balloon, ideally, flattens itself out. Okay? I will make a little note here that in the universe, there are basically two structures. There are spheres and disks. Things are spherical when the force of gravity is coalescing them from all directions, as gravity does, into a sphere. Things are disc-shaped when that first thing happens, but they're spinning fast enough that it bulges out and becomes a disk. So the two basic structures of the universe are the sphere and the disk. Either when things are relatively slowly or not at all spinning, or when they're spinning fast. And then from this accretion disk, something extremely important happens. You might even say, Some people might even say the most important thing that happens is what? No. Okay, be more specific. Not just any old explosion, what? The sun. You might say the formation or the creation of the sun. I would agree with both of those. But the sun begins to shine. Nuclear fusion occurs. A star is born. It was gas and dust. Now it's a star. I think I'm going to, I'm kind of making this up as I go along, as I almost always do, but I think I'm going to leave this diagram up, and then we'll kind of label each of these with the evidence as we come back to them. So we have the star, and everything that was in this cloud became the star? No, there was some stuff left over, and that became what? Yeah, more than just planets, but planets. Is this diagram to scale? No. We could call this protoplanets. And there should be lots of them. Basically, as this gas and dust continue to coalesce, yes, I hear the drawing of diagrams in the science room. Very good. As they continue to coalesce, they become protoplanets. And then, in what we might call a mature solar system, many of those protoplanets have themselves collided, and we're left with just a few relatively large planets, not to scale. Somewhere along the way I shifted to black, which I don't know why, but it is probably a lot easier to see on this screen too. So this is the general formation, the general trend in the formation of the solar system. Some things to think about. One, if we have our diagram of the solar system, I'm going to draw this in pink, and I want you to tell me what I'm drawing. What are these? If I'm drawing these in pink, what are they? Orbits. Orbits. Like the gum. Or the rental car. Can you think of a reason why I might have drawn this in pink? This is actually kind of a common misconception, especially among elementary age kids. Why did I draw that in pink, do you think? Because it isn't, but that's a good guess. My favorite color is yellow, and I could have drawn it in that too, but I didn't. Thank you, Ada. Guess what? That's not what we're talking about. Why do you think I drew these in pink? Besides just that it's a color that... Yes, these don't really exist. They don't have a physical existence, and that Trey's jokingly pretending to be amazed, but I think that a major misconception among even adult people might be that this diagram shows them on basically a circular string. It's very common to do that, and so a lot of people, maybe dumb people, but a lot of people think that they actually have a real existence, a physical existence. They don't. So are they real? I said they're not. They don't have a physical existence, but they are real. I mean, they do follow this line. That line itself doesn't actually have a physical existence. Okay, so these orbits, and now here's something extremely important. Which way do you guess this one goes? Think clockwise. They all go, the point is, they all go clockwise. Now, that we'll start here. This is a major piece of evidence. All objects, I'm going to backtrack a little bit, squiggly line, approximately all objects orbit in the same direction. That is a piece of evidence for this model of the formation of the solar system. Tell me why. Why would this, that all objects orbit in the same direction, be evidence that this is how the solar system formed, at least physically? Actually, I'm going to get that in the next point. Thank you for reminding me, though, Trey. But what was this? Rewind it to here. It was one more or less cohesive object. At this stage, so from here through here, they are all spinning together because the original accretion disk was spinning in one direction. Back when this was more or less one object, it was a cloud, it was a nebula, but we might have called it one object. We without jumping too far ahead, this is another piece of evidence. When we see this happen in other solar systems that we can see with a telescope, we consider those nebulae to be more or less a single object. We understand that they're made of lots of small pieces of gas and dust, but they're more or less a single object with a single spin. And so the fact that all of these, even in a mature solar system like ours, all of these orbit in the same direction indicates that at one time they were all a singular object. And I'm using that little hand gesture because, you know, they came from the same accretion disk that was spinning in a particular direction. And they continue to spin that same direction. Okay, another thing that came up, another piece of evidence that Trey had said. Yeah, he did. Doesn't know it himself. But why don't these crash into each other? Mm-hmm. Yeah. Due to gravity, which we'll talk about at length later on, and collisions, each planet has a, I'm going to put in parentheses or in quotes here, cleared orbit. In quotes. I'm putting in quotes not because it's made up, you sometimes see that, but I'm putting in quotes because we're going to talk a little bit more about that, what cleared orbit means. So, by this point in the solar system's life cycle, each of these larger objects is formed from, and therefore has removed, in a sense, the other protoplanets that it might have been sharing an orbit with. So when there were hundreds of these protoplanets, collisions, and then they have, now, when two things collide, especially in space where there's no, or very, very, very little friction, and they're only under the influence of gravity. When they collide, they now orbit with the same velocity that they had when they built their average of their velocities, and they become one single thing that is orbiting in one single path. And anytime that these orbits might have crossed, somewhere between protoplanet stage and mature solar system stage, they form a single orbit. They crash eventually and then form a single orbit. And so this is another piece of evidence that they were all one thing to begin with. Okay? Cleared orbit means that it has no other large objects in its orbit. In fact, this is one of the definitions of what makes a planet versus maybe a dwarf planet. Have you heard it? Let me tell you about Pluto. Have you heard about Pluto? Yes. Not a planet. And let me tell you why. One of the definitions that we decided on, we human beings, there's actually a larger point here, is that who decides what is a planet? Well, we can, since we're naming them, basically we do, but Pluto still exists. We decided to, as a group, we decided not to list it as a planet because of our own definitions. Stop talking, please, boys. Start taking notes and stop talking. One of the definitions that separates a planet from a dwarf planet is that if in its orbit, everything else that shares the orbit with us, so for Earth, that's Earth and its moon. For Pluto, it's Pluto and its 3 moons. If everything else that's in orbit with it has more mass altogether than it does, it's not a planet. And that's true for Pluto. Its moons, Hydra, Charon, it's named after Charon Creech, and Nix, altogether have more mass than Pluto does, and so it's not considered to have a cleared orbit, and so it's not a planet. That guy's gone. It still exists. Nothing changed about it physically, but we human beings no longer consider it a planet. Just like we human beings instituted the idea of these lines. They're in a drawing. Okay. Kind of as a whole, this idea started with a man named Immanuel Kant in the 1760s, 1780s. It'll tell me in the book if I look. Kant had an idea in the mid-1700s, the book very specifically says, had an idea that perhaps the mythical formless void that all of this formed from might have been a spinning cloud of gas and dust. And he did this kind of as a thought experiment. He didn't have direct evidence for it, but he thought about that. And one of the things that spurred him on, or at least maybe was like the granddaddy of his thought, was that recently in his life, within the last 100 years, Galileo, who we remember from Quiz Bowl, and you guys I know already know about it because someone answered a question correctly about Galileo, had observed with his telescope Jupiter and its moons. And that actually, even though to us, like, we could probably tonight go out and look at Jupiter and its moons in a telescope and be like, wow, it's a circle with some dots around it. It was groundbreaking at the time because people thought, and this is true, people thought, why would God make a planet with little moons that we can't even see? And that was like mind-blowing to the people of the time, because if we couldn't see this until we had a telescope, why does this even exist? And because of that kind of thinking, Kant got to thinking about where did this all come from, and the idea he came up with was this. But as I say, it was just a thought experiment. He didn't have strong scientific evidence to back it, and therefore it remained in the realm of philosophy instead of in what we would now call science. But we still call it either Immanuel Kant's planetary nebula hypothesis, or we call it the Kantian hypothesis, and we still more or less go off it. Sometimes it's also called the Laplace idea, because a man named Laplace came along not very long after Kant and said, the force that Kant was looking for is, guess, gravity. Because Laplace combined Newton's ideas of gravity plus Kant's ideas of solar system and came up with the idea that maybe gravity was the energy force that we were looking for. And if you're little 8th grade people, but if you were these guys, how would you test? What are some things you might look for to see if gravity can do this kind of thing? I mean, the idea was that you did that in your lab, but what are some things you might do if you were looking for this? Where else could you find evidence for this? I didn't hear what you said.
Like the natural world?
Yeah, what tools could you use to see where this is happening? Evidence. We see it in other solar systems or nebulas. Do you know the constellation Orion? I don't have room for, I think Rigel would be down here. There's Rigel. In the constellation Orion, I think this one, I might be wrong. Write a comment if you find out the right answer and it's not that one. But I think that one is a nebula. You can, with even a not very good telescope, with even a pair of binoculars, you can see it's kind of fuzzy. And with a pretty good telescope, you can see it's a nebula. And within this nebula, you can see this kind of thing happening. Over years of observation, you can see the trend of movement in that accretion disk. We can see nebulas, and so we know nebulas exist. If Kant was wrong and it didn't all come from gas and dust, we wouldn't see nebulas because they wouldn't exist. But we do. He didn't know about them, but we do see them. What else would you look for if you were Laplace or Kant or Newton to see if gravity could do this? Is there another force that we could use instead of gravity to simulate this? Yeah. Well, what did you guys do? You couldn't make glitter with strong enough gravity that they would actually coalesce. So instead, you used a model. Exactly. Let me write that word up here. Remember that a model is an idealized representation. I'm going to put flawed in parentheses. We know it's not perfect. Representation. What did you, in your model specifically, Aiden or Teague or Ada, what did you use to indicate that the gases and dust were sticking together even though you couldn't make them stick together gravitationally? They used tape. So they used some other force, in their case adhesive, to show what would happen if this was loose, without form and void, we might say, and then it started to glue together in the shape of this. They couldn't use gravity because gravity is not strong enough among glitter particles in the lab to make them coalesce, but by using tape they could show that that kind of thing would happen. That's how a scientist works. The video could be presented, the discussion could be presented as, here are the truths, and here are the people who came up with them. And that's a very common way to teach science, but I'm much more interested in you understanding that the way scientists, even past scientists like Newton was a scientist, Laplace was a scientist, Kant, I don't know. But even the way these guys did it, Galileo, they used the same things you did, models and observations and evidence, arguments from evidence. And so it's the same kind of thing. And in my opinion, you becoming a scientist is much more important than you regurgitating science information. Let's talk now a little bit about one other piece of evidence for this. That where is most of this? now. So this existed in the past. In a sense, it still exists, but it looked like this in the past. Not quite like this, because this is an idiot's drawing of it, but it looked something like this in the past. Where is most of this now? No. Yes, almost all of it. Much more than 99% of it is in, much more than 99% of it became the sun. Hold on real quick. I'm going to go get the model that the Earth scientists made. Okay, check it out. I have kind of memorized. I'm excited to show you what Leah and Allison and Kylie and Isaiah have come up with for their version of this. But I have this kind of memorized, and I want to talk about it with you. So in the model solar system that my Earth scientists made, this was the sun, and these are to scale. So this is the size of the sun. This is the sun. The next one, actually, let me tell you this. Yep, Earth is the next one. No, that's totally false. Mercury and Venus got destroyed, and so did Earth. So we're just going to skip those. But at this scale, they did the math, as these people are doing, and at that scale, this is the size of Mars. You see it? It's red like Mars. Will you tell me if this is showing up on the camera, Tiana? It's going to be, but you can see it. It's like in the frame, but it's small. Yes. So that's the size of Mars. And let me see if I can remember the exact amount. I think this one was 70 meters away. 70 meters. You know how far 70 meters is? Well, you know how far, if you've ever played six-man football, you know approximately how far 80 yards is. We'll say they're about the same. So how far the entire length of the football field is how far Mars is away from the sun. But this one's Mars. I'm just going to set him right here real quick. This is, yes, the largest planet, Jupiter. The largest planet, Jupiter. Real quick, look at the solar system model on page 75 and see if you can find any flaws with the solar system model on page 75, which is probably the one you've been seeing pretty much your whole life. It's, yeah, colors. What else? Scale is exactly the problem. In fact, many models, their major flaw is scale. So this is Jupiter. Saturn's next, and they made these rings to scale too, so that's kind of beautiful actually. The ring is a paperclip, but that's Saturn to scale. Uranus. We don't say it like that. Neptune. These together, by the way, do you still see them on my... do you see them still here? These together are called the giants, right? This is Jupiter, a gas giant. Just sit here. Just sit here. Jupiter, a gas giant. Saturn, a gas giant. Uranus, we call these sometimes ice giants, but these are all together, the four of them, gas giants. And are they giant? Not compared, because I'm sure the mass isn't to scale, their diameters are to scale, but pretty close. If I were to smoosh all these together, including what was Earth and Mars and Venus, they're not. This is nothing. I would say this is less than 1%. This is probably less than 1% of, not the diameter, but the mass, certainly. Yeah, they're gone. And this is the reason there is no more Mercury and Venus and Earth is that I had them laid out to show this to you, and someone who won't be named, but they're Hunter Owens, came in here and was just like kind of rolling this around just for fun, and they completely absorbed Mercury and Venus and Earth. They're just gone. And that's really real for how the scale is here. Like, it's almost, a word I learned recently is sublime. It's almost beautiful in a disturbing way how big this is compared to the rest. And then let me tell you more about the space between them, because the other problem with scale on your picture on page 75 is that it looks like, here's the sun, pretty big, and then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto somewhere over there, right? But that's not it at all. When we did this, I don't want to do it like this because I want to show you in real life, but the scale was insane. When we did Neptune, we were in, this is not a joke, if you think about across the highway, in the middle of that field, and now I'm outing myself on live television, we were in the middle of a field. We had to hold down a barbed wire fence almost a mile away from the school to put Neptune where it belongs. Do you remember the size of Neptune? I smooshed it, but it was that big, almost a mile away from the sun. The space is mostly empty space. The next thing, I think this will be the last thing. I had a couple other things I wanted to say, but I know we're running out of time. Some of us need to get going, but something, I'm just going to write this down, and I want you to remember this. The universe is all of physical reality, everything. What is within the universe? What's the next biggest thing down, do you think? No. Galaxies. Galaxies are groups of stars. Next biggest down? Solar systems, which are a star and its little buddies. Stars, planets, and then of course it goes down from here. Somewhere down here is Ada Norman and her friends. But this is the order, right? And if this is something actually the book considers this to be very important, that you know that this is the order, because some people don't. Some people are like, you're my best friend in the galaxy, and then they're like, well, what about other galaxies, baby girl? And the answer is that there are a lot of galaxies in the universe, there are lots of solar systems in each galaxy, etc., etc., etc. I think I have two more questions for you. Are you ready for these two questions? One, that was going to be too open-ended. Do you think it's a coincidence? And I'm going to tell you the answer is already no. Why don't you think it's a coincidence that, I've destroyed my model and I don't have any room to draw a new one. I'm going to do it right here. Is this model going to be to scale? Can you already tell? In order, this is the sun. That's the sun symbol. I love these little symbols, so I'm going to show them to you. This is Mercury, is like that. Venus is like that. Earth, Mars. You might recognize Venus and Mars. Do you recognize those symbols?
Yes.
What are they? Male and female, yeah. So Venus is the female symbol, Mars is the male symbol. Mercury, or Jupiter's looks like that. Saturn's looks like that. Uranus, I keep meaning to look this up. I think it's the male symbol, but with a dot in it. And then Neptune's is Neptune's trident. So this is the order of the planets. The sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Do you think it's a coincidence that these four, the terrestrial planets, are all nearest the sun, and the four further away are the gas giants? Do you think that's a coincidence? I'm going to tell you the answer is no. Why is that not a coincidence? What went on in this accretion disk or in the protoplanetary system that the terrestrial planets are all towards the sun?
Because they're smaller.
What are these ones made out of?
Yes.
If these were going to be made out of gas, where did that gas go instead? The sun. That's exactly it. So the sun was absorbing all the gas, and the sun, you might remember this from being outside. The sun's very hot. The sun absorbed all that gas, and the heat from the sun caused mostly materials with high melting points to make up these interior planets. Okay? So that's one point I wanted to make. And the other question I have for you, that I will remember when I get to the page that I had it on. Why do all of these things move through the sky? What is the primary reason for that? Is the sun actually moving? Goodbye. Is the sun actually moving? Be careful. The answer is yes. But is the sun actually moving across the sky every day?
No.
What's the real cause for that apparent motion? Yeah, the Earth's rotation makes it seem like the sun moves through the sky. What makes it seem like the planets move through the sky? The Earth's rotation. But also the planets themselves revolve around the sun. And so sometimes it seems like, if you're looking at it from the planet or from the ground, it seems like you're looking at Mars every night at 8 a.m., 8 p.m. You're looking at Mars, and then it seems to go backwards for a night, and then it starts going forwards again. This motion here, you might have heard of this if you're an astrology girly, is called retrograde motion. Retrograde means going back. Retro, like retro, if you have retro pants on, they're from the past. Retrograde means going back. And this is apparent motion caused by the fact that we're seeing it on a nightly basis different because the Earth is rotating, but also it's moving in its orbit. And so that causes what seems to be retrograde motion. Why do the stars seem to move every night? Because the Earth is rotating, generally. Generally. Do the stars actually move? Sure. But generally the way we see their motion is apparent motion caused by the motion of the planet Earth itself. And one of the points that your book points out is that there's a difference between relative measurements and absolute measurements. You might remember this when we talked about fossils. Absolute age dating was saying how old it is. Relative age dating was who's older or younger. You remember that? Same thing with other measurements. Relative length versus absolute length. Relative motion versus absolute motion. All right, I love it. Chaos, and then it becomes order. Goodbye.